All right, so on this next little page right here, so this is just a little side note here. If negative c denotes a curve with the same points as c but in opposite direction, so what that's telling you right there, kind of like if we were doing this picture right here, like if we said to you, hey, instead of going from here to here, go here to here. So it's like, backwards, all right? It says then if you're integrating with respect to x or y, then basically that your equation is going to be backwards, right? Because if when you subtract going the other way, we would have gotten all these values here. This would have been negative t and negative 4t and negative 5t right there, and so you would get a backwards. It would go backwards, all right? And so, but when you integrate with respect to arc length, it doesn't matter, basically. Arc length, it doesn't matter which direction you're going. And so that's just a little side note if you ever see that. It won't really affect you doing your problems or anything like that. So an important application of line integrals is using them to find the work done in an object moving in a force field. Okay, so work done by a vector field basically on an object as it passes through the field. And so that is the work, right? So it's the work done by the vector field on that object when it's traveling through that vector field. So in a way, like you think of it as, say like you're traveling along this path, these little red little vectors are your vector field that we drew in section 17.1 or 16.1, sorry. And so when we find the work, it's like if you had an object moving along this path, how much work would it have to do? All right, and so there we go. So when you do the formula for work, it is a line integral, and it has three different ways that you can write it, but the way that we're going to use it is this piece right here. This is the one that we're going to use. And notice right there that this inside here is the dot product, all right? So the one that we're going to use is along curve C. We have F, so that's our vector field, right, of RT. So RT is our path that we're traveling along, and then times or dot product with R prime of t. So it's very similar to the first problem, that the first type of line integrals that we did, and then of course dt back here. Notice that's a dot product. So you have to set it up, you have to find r of t, r prime of t, you have to dot your two vectors together and everything. So here we go. All right, so here is our big F, right? So another way to write this big F is to separate it out. It's written out in standard form, but we can write it in component form. We put, x squared, comma, and then this is negative xy. That might be a little bit more understandable when we go to write our vectors. All right, so we have, we're moving along a quarter circle. So it's just, a circle with radius 1, and it is only in the first quadrant. That's why you see 0 to pi over 2. So when we calculate our work is 0 to pi over 2. All right, but let's make up some of our problems. So our r of t is cosine and sine, cosine t and sine t. Now let's go ahead and do our derivative. So I get negative sine t and cosine t. Okay, and why don't I also plug that into my f? Right, I have to plug that into f. So for x squared, I'll get, I'll have to square the negative sign, so I'll get sine squared. And negative x times y, I'm going to get, oh my gosh, I did that again. I was using the derivative. I wasn't supposed to use the derivative, I was supposed to use the original. I was get cosine squared, sorry. And then I'll have to do negative x times y, so I'll get negative sine times cosine, or cosine times sine. Okay, all right, so our work is going to be the dot product of this vector force field with our t's plugged in, or our like r of t plugged in. So that's going to be my cosine squared, comma negative sine t cosine t that I figured out, dotted with r prime of t. So r prime of t is the negative sine t that we figured out, and cosine t. So you see, it's good to get those things set up beforehand so that you can just like do it, all right? And d of t over here. All right, so now we just have to work this out. 0 to pi over 2. So let's do our dot product first. I get cosine of t times negative sine of t, or cosine squared. So I get sine t negative, let's see, cosine squared t. And then dot product means I add the multiplication of the last two, so that will be minus, and I have a cosine t, and that's going to be cosine squared, right? And then I have sine of t. And dt, put some parentheses around that. All right, so these are both sine and then cosine squared, right? So there's two of them. And so I'm going to go ahead and do this integral. I'm going to pull out the negative and then put a two of them because there's basically two of the same thing right here. Integral 0 to pi over 2. And I can just write it once, sine t and then cosine squared t. And we did an integral like this earlier. Remember, we had to use u substitution, so we let u be cosine t. And that way my du was negative sine t dt. So when I do my integration, I have the integral. I have basically u squared, and I put a negative out there to counteract for this negative here, and I have dt. So I get u to the 3 over 3. It's negative. And remember, my u is cosine. So I get negative cosine to the third over 3. Okay. So if I put everything back together now, I have a negative, and I have another negative 2, so I have a positive 2. Excuse me. And I have, let's see, a 3 under there, and I have cosine to the third. I'm going to evaluate this from 0 to pi over 2. Now, at pi over 2, the cosine is 0, so that's going to give me a 0 minus, and then when I plug in 0, the cosine is 1, so minus 2/3. So my answer is negative 2/3. So this is the work done. And so what this is telling you is up in this little caption right here. So figure 12 shows the force field and the curve in example 7. All right. The work done is negative because the field impedes movement along the curve. Okay. So the vector field is not helping you move, it's acting against you. And so that is your work. All right, and I'll see you next time. Bye-bye.